Gracias, Leobardo. Muchas gracias a todo el comité organizador por invitarme a platicar unos minutos en este 16º taller. Bueno, lo que podría decir es que nunca, desde que comenzó en 2006, nunca lo hemos suspendido. Se ha realizado todos los años. Yo formé parte del comité organizador hasta 2019 y no es porque no haya querido organizarlo durante la pandemia, sino que por casualidad dije suficiente. Y por fortuna hubo quien tomara la estafeta y que han seguido organizando. Algunos ya estaban desde mucho antes, Leobardo, Patti Pellicer, David Maya, y recientemente pues se incorporaron Yaciel y Alice, lo cual me da mucho gusto. Y están haciendo una excelente labor. Lo que dice Raúl me parece muy interesante. Realmente cuando el taller era presencial, pues no teníamos esa variedad de América Latina y de todos los estados de la República. Siempre tuvimos mucha participación en los talleres presenciales, pero ahora pues a ver qué, cuando vuelva a ser presencial, a ver si podemos también hacerlo de las dos maneras, presencial y en línea estaría, porque de esa manera pues tenemos nuevos participantes. Bueno, pues esencialmente quiero agradecer a todos los que han participado en los diferentes comités organizadores y especialmente al actual comité organizador, que ha hecho un gran esfuerzo por organizar este 16º taller. Y estuve viendo el programa y me parece muy interesante, con muchas pláticas sobre teoría de continuos, otras tantas sobre sistemas dinámicos, y creo que el taller sigue siendo un éxito y una oportunidad para que los estudiantes tengan un foro para discutir sus temas de tesis, sus temas de tesis de licenciatura, de maestría, de doctorado. Y aunque no es la misma convivencia que había en los presenciales, creo que algo les ofrece de convivencia esta modalidad en línea. Pues muchas gracias a todos por estar aquí presentes y espero que ya comencemos con el programa.
Muchas gracias, Betty. Muchas gracias por tus palabras. También a ti, Raúl, muchas gracias. Supongo que ya falta un minuto, pues déjenme presentar a Benjamin Vejnar. I'm sorry again, Benjamin. I will talk in Spanish a little bit more, but after that, you can start. But let me introduce you in Spanish. Benjamin hizo su doctorado en Charles University en Praga. Se doctoró en el 2013. Y después de eso, bueno, entró como profesor, assistant profesor, ahí mismo en la Universidad de Praga. Y ahora ya es profesor asociado. También fue distinguido con el premio Neuron, no sé cómo pronunciar eso, que es para los jóvenes prominentes. Pues bueno, un premio que le otorgaron en el 2018 y ahora pues hace investigación en teoría de continuos y un poco en sistemas dinámicos. Entonces, bueno, es un gusto para mí presentarles a Benjamin Vejnar y el título de su plática lo tengo aquí, es Descriptive Set Theoretical Properties of Continua. So, Benjamin, the screen is all yours, and let's start with this conference, with this workshop.
Okay, thank you very much. So, first of all, let me share the screen. Okay. Is it okay? Can you see it?
Yeah.
Okay, great. So once again, thank you very much. First of all, I should say that it's a great pleasure for me to give a talk in such an audience. I am very glad to see that there are so many people in Mexico who are interested in topology or dynamical systems, continuum theory, or hyperspaces, say. So I'm really glad for this opportunity. Well, so my talk is called Descriptive Set Theoretical Properties of Continua. So I should say that in this talk, I will use descriptive set theory as a tool to study continua, okay? Since this theory is somehow well established in mathematics, it is studied on its own, but I'm rather interested in their applications to continuum theory. Okay, so first of all, let me start with just one basic elementary question. Okay, which serves as a motivation of all of this. So the question is whether there exists a compact space X such that every continuum is homeomorphic to a component of this space. Okay, so you can think for a few seconds about this question, knowing the answer is yes. How to prove that such a space exists? Okay, so I can give some hints. Well, let me just denote by Q the Hilbert cube, 0, 1, countable power of this. And let denote by C the Cantor ternary set. Now, we also consider the hyperspace of all subcontinua of the Hilbert cube Q. Okay, and by a well-known fact, every compact space is a continuous image of the Cantor set. So there exists a continuous mapping say phi going from C onto this hyperspace of all subcontinua of Q. Okay, this is what I forgot to write, that CQ, this is the hyperspace of subcontinua of Q. Okay, and now we can just consider the following set. X be defined as the set of all pairs X and Y in the product of the Cantor set C and the Hilbert cube Q, for which Y is an element of phi X. I will draw a picture. So we have this Cantor set C here, say the Hilbert cube Q here. And now for every X in the Cantor set, say X is here, we consider all the possibilities Y which belong to phi X. Now that phi X is some subcontinuum of Q, so we put all the points X, Y here. Okay, and this is for every point X. So it can look like this. But of course, these vertical sections could be very complicated. So now we can check that components, or well, first of all, we should check that X is closed in this product C times Q. This is actually a consequence of continuity of phi. And since this product C times Q is compact, X is compact as well. Well, moreover, if you take any continuum K, you can find a homeomorphic copy, say K prime, in Q, a homeomorphic copy of this K, right? K homeomorphic to K prime. But since this phi is onto, okay, which this is something what I said but forgot to write, is onto, we can find some X, a point in the Cantor set, such that phi of X equals to this K prime. So we found this X, we have this K prime here, and it's easy to check that this is in fact a component of in the space X, right? So in this way, we constructed a compact space such that every continuum is homeomorphic to some of its components. But well, we can make the question a bit more difficult. We can additionally require that no two components are homeomorphic. So is it still possible to construct such a compact space? Well, the answer is negative, but actually the reasons are not so easy to describe, but probably at the end of the second lecture tomorrow, I will be able to describe at least some reasons, or I will sketch the proof of the negative answer to the stronger question. So this is like a motivation. Now let me continue more seriously. So the first part of today's talk will deal with complexity of sets, and there will be two subparts. First of all, we will consider sets of points, mainly in continua, and we will consider their complexities. So this is like the basic level. And on the upper level, we will consider families of continua, and we will consider the complexities of these families, usually considered in the hyperspace of the Hilbert cube, for example. And tomorrow, we will study complexities, but not of continua or sets, but complexities of relations. Okay, we will first study relations between points as the basic level, and then as an upper level, we will study relations between continua, mainly the relations given by homeomorphisms. Okay, so the part for today is complexity of sets, and we will start with sets of points. But first of all, I need some basic stuff from descriptive set theory. So this is what will follow now. So first of all spaces are metric or metrizable, and a Polish space, this is any completely metrizable and separable space. When talking about complexity of sets, we deal with Borel sets, most of you probably know that Borel sets, these are sets which form the smallest sigma algebra, which contain all the open sets. Okay, so this is kind of a description from above, because we are talking about minimal sigma algebra, which contains open sets, but we can build up Borel sets from below. Just starting with open sets, of course, we need complements, so we need to add closed sets as well. But we need to add countable unions and intersections. That's why we consider sets of type G delta. These are just countable intersections of open sets, or sets of type F sigma, which are countable unions of closed sets. And we can continue this process. So F sigma delta sets, these are just countable intersections of F sigma sets. G delta sigma are countable unions of G delta sets. And of course, we can continue inductively, but even we can continue transfinitely. Okay, in fact, we don't need to go into the details because most of the classes that we will study are actually G delta F sigma, or one of these two, F sigma delta or G delta sigma. Okay, so this gives us some kind of hierarchy of sets. Open and closed, these are like simpler. F sigma, G delta, these are more difficult. F sigma delta, G delta sigma, they are even more difficult, and so on. We can continue transfinitely. Well, but then there are also much more difficult sets, which are called analytic and co-analytic. So analytic sets, these are defined as continuous images of Borel sets in Polish spaces. So exactly by the definition, of course, we can see that every Borel set is analytic. And co-analytic sets, these are defined as complements of analytic sets in Polish spaces. Well, I should write some examples. So for example, if we consider rational numbers as a subset of the real line, then this is a set of type F sigma, but it is not of type G delta. So it follows that if you consider irrational numbers, then these are G delta, but not F sigma. Well, and there is a fact that every Borel set is analytic as well as co-analytic, and even it holds that if you have a set which is analytic and co-analytic, then it is Borel. An example of a set which is co-analytic but not Borel is the following. You can consider all the countable subsets or countable closed subsets of 0, 1 in the hyperspace of all compact subspaces of this interval. Okay, so this is an example of a co-analytic but not Borel set. Okay, so now let me give few examples of sets, and we will just examine its complexity with respect to this list of complexities. So I will just talk about components, composants, and path components. So let me start with components. This is the most simple case. Well, every component of a space is just a closed set. Okay, this is a very simple fact. I think that it is well known. Well, it follows just by the fact that closure of a connected set is connected. Okay, so components are simple because they are closed. That's it. Well, what about what about composants? So a composant of a point x in some continuum x is defined as the union of all proper subcontinua which contain the point x. So for example, if you have this closed interval 0, 1, then composant of this point 0 is just the half open interval 0, 1. If you consider the point in the middle, then the composant of such a point is just the closed interval 0, 1. Okay, but composants are mainly interested in the composable continua, where it is known that every composant is dense. Well, just by the definition, it is not completely clear whether composant of a point is even Borel, because it is defined as some union, but it is not a countable union. There can be a lot of proper subcontinua which contain this point x. But it can be shown that actually every composant of a continuum is of type F sigma. So let me show the details how this can be proved. So first of all, we consider a continuum x and a point x in x, right? And we denote by Cx the composant of the point x. In this continuum x. So what can we do? We can consider a countable base of open sets of the space x minus the single point x. And now for every n, we let Kn be the component of the point x in the space x minus Bn. Well, we already know that components are closed, so this Kn is in fact a continuum. And it's not difficult to check that if we consider the union of all these Kns, then actually we get the composant of the point x. Okay, so we were able to express, sorry, the composant. We expressed composant of the point x as a countable union of closed subsets. So it follows that Cx is of type F sigma. It is a countable union of closed sets. So its complexity is somehow under control, say. Okay. So now let me continue to the most difficult case here, which is path components. Well, it is known that every path component of a continuum is analytic. So again, in order to express the techniques, let me sketch the details. Well, so again, we have a continuum X and a point X here, and we consider its path component. Okay, maybe I should say that the path component is just the set of all points Y, which can be connected with X by a path. So by a homeomorphic copy of closed 0, 1. So we can consider the following collection, P. We let P to be the collection of all subcontinua of X, which are locally connected. So P is a Peano continuum. And X is in P. Well, it is an exercise to check that this is a Borel set. It is a Borel subset of the hyperspace CX. And now we can consider the following. M be the set of all pairs Py, where okay, P is a Peano continuum, a Peano subcontinuum of X, and Y is some point in X, such that this Y is just in P. Again, this is a Borel subset of the corresponding product P times X. And we can consider its projection to the second coordinate. So we consider this projection going from the product P times X to X, and we consider the image of this set M. So what we get, well, we know that every Peano continuum, of course, is path connected. So we get that this projection is in fact equal to the path component of the point X. In this space X, right? So the picture is like, okay, here you have this set P, here you have this maybe not path connected space X, here you have some point X, and now for every P here, you just consider this Peano continuum here, which contains this point X. So the picture is similar to that one that I draw at the beginning. And now we consider the projection which goes in this direction, this projection. So what we get, the image would be the path component of the point X in X. Well, of course, the projection is continuous. And since we know that this M is a Borel set, we obtain that the path component is analytic. So again, we have some control, but actually there are known examples of continua in which a path component is not Borel, right? So it is analytic, but not Borel. I think there are even continua in which every path component is non-Borel. On the other hand, okay, if you consider planar continua, it is not known whether whether there is a planar continuum with a non-Borel path component. This is an open question. So in planar continua, we don't know whether it can be simplified to the Borel case, in fact. Well, I will skip this node here, and I will continue by the next slide. Okay, so now I will just talk for a while about dendrites. So dendrite, this is just a locally connected continuum which does not contain a topological copy of the circle. And endpoints in continuum, this is just a point of order 1. This means that being of order 1, this just means that there are arbitrarily small open neighborhoods whose boundary have only one element. Okay, and we can consider a dendrite and its set of endpoints. Well, it is known, and it is one of the exercises, that the set of endpoints in a dendrite is always of type G delta. Of course, it can be of a simpler type as well. For example, for trees, the set of endpoints is finite and hence it is closed. But in general, there are dendrites where this is not enough. So in general, the set of endpoints is G delta. Well, actually thinking about Waschewski dendrite with respect to this theorem is quite helpful because it implies that endpoints in the Waschewski dendrite, being an endpoint, is somehow typical. Okay, so let me just recall that the Waschewski dendrite is a dendrite which contains a homeomorphic copy of any other dendrite, and it can be described as follows. We just start with an arc and we add a null sequence of segments to some point. And we continue in this process by adding smaller and smaller copies, say in the middle of the longest free arc here. So we get a picture like this. Of course, this is just a countable process. So if we want to get a continuum, we need to consider the closure. And by considering the closure of this countable union, we get a lot of endpoints here. So in fact, what we draw here is just a very small portion of the dendrite, right? Because the rest, what we will get in the closure is this G delta set of endpoints, and in the Waschewski dendrite, the endpoints are dense. So we get that it is a dense G delta set, and you know by the Baer theorem, this is a really big set. You cannot have two disjoint dense G delta sets in a Polish space. So it resembles somehow the case when you draw the Cantor set. You just start with these points and you are adding points with respect to the deleting middle thirds. But of course, what you draw is just a countable set, say, but you need to consider the closure. And again, the points that you get in the closure, this is a dense G delta set. So this is actually most of the space, most of the Cantor set. So it is similar here with the Waszewski dendrite, that what you are drawing is something very small from the topological point of view. Okay, so now let me proceed with dendroids. So let me just recall that a dendroid, this is a path-connected continuum in which the intersection of two subcontinua is always connected. Okay, so it is hereditary unicoherent. And where the notion of endpoint that was used in dendrites is not completely suitable for dendroids, there is actually a better or another definition that is most suitable for dendroids. This is the endpoint in the classical sense. And it is just a point which is an endpoint of every arc in which it lies. Well, and again, we can deal with the complexity of the set of endpoints. And there is the following result by Nikhil and Timchatin, that the set of endpoints in a dendroid is a co-analytic set. This is actually not so difficult to prove, but what is non-trivial is that there is a dendroid whose set of endpoints is not Borel. Okay, so it cannot be in general simplified to Borelness. Okay, so this is an example of endpoints in dendroids. Of course, I am not going to prove these results because they are more difficult than the previous ones. And now let me proceed by, or let me proceed to this upper level I was talking about. So till now we were interested in complexities of subsets of continua. But now we will consider a family of continua, and we will ask what is its complexity in the corresponding hyperspace of the Hilbert cube. So first of all, let me say that every continuum can be supposed or has a homeomorphic copy in the Hilbert cube. So if we consider this hyperspace of all subcontinua of the Hilbert cube, then we can just consider that it contains up to homeomorphism all continua. Okay, so now given a family of continua F, we can ask what is its complexity in this CQ. Well, so there is this result by Kuratowski, which is actually one of the exercises, that if you consider Peano continua, then these form an F sigma delta set in the hyperspace of the Hilbert cube. Well, this can be proved by using the idea that Peano continua are described by the property that for every epsilon, you can find a finite cover of the continuum by continua whose diameter is less than epsilon. Okay, so, and this is actually good to know that if you want to prove that some class of continua has some complexity, usually you need to find some good characterization, some kind of simple characterization. Okay, there are another results of this kind. Well, chainable continua as well as tree-like continua are G delta, and dendrites are of type F sigma delta. So for example, here for this result for dendrites, we can use the following characterization. Dendrites are known to be continua, which are tree-like, right? So since we know that continua are F sigma delta and tree-like continua are G delta, it follows immediately that dendrites are F sigma delta because they are continua and tree-like continua at the same time. Okay, so now proving that chainable continua and tree-like continua are G delta, this is again one of the exercises. Okay, so let me again continue with dendroids. It was proved by Camerlo Darci and Marcone that dendroids form a coanalytic set in CQ, which is not analytic. Okay, so it expresses somehow the feeling that dendroids are much more complicated than dendrites. The collection of dendrites is Borel, it is F sigma delta. It is quite nice. But dendroids are much more difficult to handle with, and well, they are coanalytic and not analytic. There is another result dealing with dendroids proved by Krasinkiewicz and Mintz that there is no universal dendroid. Well, in fact, Krasinkiewicz and Mintz proved their result much earlier, but their proof was somehow by hands. But there is a more conceptual proof which can use this result by Camerlo Darci and Marcone to prove that there is no universal dendroid. So let me present the details how this can be done. Okay, so we are going to prove this corollary using this theorem. So suppose for contradiction, that there is a universal dendroid. Say D. And let us consider the following set. Say S. This will be the set of all injections phi going from C to the Hilbert cube Q, where phi is injective and this C is a subcontinuum of this D. So this C is some dendroid, right? So now this set S can be considered with a very natural topology in which we get that it is a Borel set. And we can consider the following mapping, say phi, big phi, defined on S to the hyperspace of the Hilbert cube, and it will be defined as follows. Well, phi, when applied to some small phi here, will be nothing else but the image of phi. Okay, or maybe it's better to write it like this. It's okay. Just image of phi. So this is some subcontinuum of Q, and it will be, this phi will be continuous. So the image of this big phi, this is just a continuous image of a Borel set. So this is analytic. And of course, this phi of S is consisting of all the dendroids in the Hilbert cube. Okay, so what we get is just that dendroids are analytic. But this is a contradiction with this theorem by Camerlo, Dargi, and Marcone. Contradiction. Okay, so we can see that a descriptive set theoretical result, like the dendroids are not analytic, has a very nice application in the continuum theory itself, that there is no universal dendroid, right? This application here. So now, the last thing I would like to mention here is dealing with homogeneous spaces. So let me recall that a space is called homogeneous if for every pair of points x and y, there is a homeomorphism of the space into itself, which maps the point x to the point y. Well, there are natural examples of homogeneous spaces. So for example, the simple closed, the circle is a homogeneous space. In fact, every topological group is a homogeneous space. But for example, the closed unit interval is not homogeneous. Because you cannot find a homeomorphism which maps the point 0 to the point 1/2, say. And recently, Pavel Krupski proved that the family of homogeneous continua is actually an analytic set, right? So this is a very nice result, because before that it was not known whether there is such a nice bound. On the other hand, it is still open whether the family of homogeneous continua is Borel. Well, there are some partial answers. for example, if you consider just homogeneous continua which are in the plane, then the answer is yes. This follows by a recent result by Logan Hahn and Lex Overstegen, because they proved that planar homogeneous continua are in fact classified, and there are just few types of these continua. In fact, it is either a point or a circle or so-called pseudo-arc, or the circle of pseudo-arcs. And since there are only these four types, actually it's easy to prove that the collection of each of these sets is a Borel set, and thus all planar continua, planar homogeneous continua form a Borel set, right? But in general, the question is open whether homogeneous continua form an analytic set. Okay, so I think that's it for today. I can stop a bit earlier and I can continue tomorrow with the second part of the lecture.
Okay, thank you very much. There are some questions in the chat. I will tell you that Gerardo Acosta asked, what about the class of Kelly continua? Do you know something about it, or?
I don't know immediately.
Ah.
I think definitely something is known, but okay, I can try to find something, or but just at the moment I don't know.
Yeah, okay. Yeah. Chicos, ¿hay más preguntas para Benjamin? Are there any more questions for Benjamin? There is another question in the chat. I don't know if you can see the chat, Benjamin, or?
I should, yes, I think I should be able to see it.
Let's see.
Okay, for the half homogeneous continua, yeah. I think that it is not known. I haven't seen any result of this kind dealing with half homogeneous continua.
And also 1/n continua, I guess.
Yes. Perhaps it will be more complicated than homogeneous, I think. Yeah. So since this is open, but okay, I don't know whether, for example, half homogeneous continua form an analytic set. This could be an interesting question.
Okay. Is there any other question? ¿Hay más preguntas, chicos? Well, it seems there are no more questions for today. So, bueno, agradezcamos a Benjamin. Let's say thanks to Benjamin for today. And I don't know how to do this here. I don't see my claps hands in here.
Perhaps I should stop sharing.
Okay. Okay. Well, thank you very much, Benjamin, for today, and see you tomorrow.
Okay, thank you very much. See you tomorrow. Bye-bye.
Bye. Sí. Yes. Chicos, hay material de los cursos